Hi, this is ET370 Lecture 7. This is the first part of a two-part lecture. We're going to talk about MOSFETs. So in this first part, we'll introduce MOSFETs. We'll go over the symbol construction, get some intuition by looking at the water analogies, and then take a closer look at the NMOS specifically. In the second part, we'll break out the NMOS and PMOS and look at their states and examples. But let's just look at a MOSFET. And a MOSFET is just a three-terminal transistor. And here's an example. This is a little inverter that I made to control a brushless DC motor. But here's 6 MOSFETs right here. And I think you can see it right there. You can see the 3 terminals. And very similar to a bipolar junction transistor, where you have an input signal, a low power input signal, and you have basically 2 power terminals, right? So that's going to allow the current to flow. Okay, so this is a little example using 6 MOSFETs to drive this brushless DC motor. Now, the MOSFET word, or the acronym, stands for metal oxide semiconductor field effect transistor. And what we'll see is that the field is going to be able to create a conductive channel, and the metal oxide is the reason why it's voltage controlled as opposed to current controlled in a bipolar junction transistor. Okay, so if we compare it to a bipolar junction transistor, a MOSFET actually has faster switching, right? So you can oscillate much quicker than a bipolar junction because you don't need to get current to turn on and turn off. So it has simpler gate drivers, more efficient because you don't have to draw that current. And but it's more expensive, right? Typically, but the costs are going down, right, with the prevalence of MOSFETs. Because you have this metal oxide, you actually have capacitance that you have to deal with. And they're typically made for lower voltage applications when compared to the bipolar junction transistor. Now, one thing to note is that the resistance increases with current. So there's less chance of a thermal runaway, unlike a bipolar junction transistor, where as more current flows through, the resistance actually goes down, which pulls more current. So you get this thermal runaway effect with bipolar junction transistors, as opposed to MOSFETs. So that's kind of nice. Okay, so let's look at the symbol and construction. So there's 2 types, just like a bipolar where it had NPN, PNP. Well, we have NMOS and PMOS. And so you still get the NPN-like flavor, right? You get a piece of semiconductor with doping such that you have an N, a P, and N. Okay, so then you have the metal here, a conductive plate of metal attached to what we call the gate, which is similar to the base, right, for a PNP. And then you have an insulated oxide layer right here and that I have in hash marks, all right? And so here's the symbol, right? And notice also I forgot to mention this body. This is another like conductive plate. So you have the gate, the drain, the source, all right? Gate, drain, source. And notice the source is attached to both the bottom end and the body, okay? Now, the gate is like the base, the drain is like the collector, and the source is like the emitter, right? So I hope you see a lot of similarities between the bipolar junction transistor and the MOSFET. Okay, and like I said before, the body and the source are connected. So this is the symbol, and this is the construction. Okay, so for the PMOS, it's kind of like the dual, right? You can see the source is now on top, right? Just like I used to draw the emitter on top for the PNP, and you do have a PNP-like flavor going on, right? The construction. Okay, so you still have the oxide layer, you still have the metal, but you have the gate in the middle, drain on the other side, and the source here. And again, the arrow is attached to the source, just like the arrow is attached to the emitter, right, on a bipolar. Now, notice something that you're just going to have to memorize. Look at the arrow directions. Remember we had not pointing in? Well, what's going on here? This arrow is pointing in for the NMOS. So the arrows are opposite of a bipolar junction transistor symbol. So the way I remember it is I go, well, I can remember not pointing in, or I can remember pointing in proudly for a bipolar. And I just remember that the MOSFET is opposite. So if I see pointing in, I'm like, oh, it's the opposite. I got to do this little kind of calculation in my head and go, okay, that's an NMOS, right? All right, so just remember that. Okay, so again, let's just repeat some observations that we can see from here. S is attached to the arrow, just like the emitter. G is the middle, it's like the base. D is the third lead, whatever's left over, okay? No gate current because you have this oxide layer, but you do have a base current when you have a BJT. But here, voltage controlled, no gate current. But I hope you can see that this is why you have that capacitance issue, right? Because essentially you have an insulator, and if you have charge, you can have charge buildup. Okay, now ID is attached to D, Okay, so this ID is attached to D, but really it doesn't matter because this ID flows all the way through by KCl, right? Okay, and it follows the arrow in the symbol. Okay, so out and down. Okay, all right. So NMOS arrow in, ID in. Okay, PMOS arrow out, ID out. Right, so arrow out, ID out. NMOS arrow in, ID in. If that makes sense. Okay. All right. So let's look at the hydro water analogy to see if we can get a sense of how this works, right? So I redrew the symbol, okay? And here is my imperfect sketch of a hydro analogy. Imagine a pipe, okay? And remember, it's voltage controlled. So voltage is like pressure. So I have a pipe. I have high pressure at the drain, low pressure at the source, okay? So that's just kind of always going to be there under normal operating conditions. And now I can apply a pressure at the gate relative to the source. And imagine this elastic membrane in here. And imagine the spring-loaded plunger. And if I apply pressure, the spring-loaded plunger is going to open up this channel here and allow current to flow. However, if this pressure is not there, the spring load is going to push that plunger to the left and block the flow. Okay, so the flow is controlled by this gate voltage. So high gate voltage, more flow. That's basically the concept of it, right? And very similar to the bipolar junction transistor. If I got current to go in, I get flow. So I hope it's a pretty simple understanding or intuitive understanding of how this works. Okay, PMOS is kind of like, you want to think kind of opposite logic. I've noticed again, I've flipped the sources on top, drains on the bottom, but still current we want to run in the same direction. And here is my hydro analogy. So imagine just the elastic membrane here. So in this case, if I have high pressure here, what happens? It blocks the flow. And if I have low pressure, it opens up. So reverse logic to this one. Still high pressure, low pressure, right? I want current to flow down, but the way I'm activating it is opposite. Here, I need high pressure to activate it. Here, I need low pressure to activate it. Okay, so low gate voltage gets more flow. All right, so let's finish up the last part where we're just going to do a deep dive on just the NMOS and look at the three different states. So the three different states that we're going to look at are, I'll even put them here, cutoff, triode, and saturation. So cutoff is going to be like NPN cutoff. Now, again, you're just going to have to memorize, this is kind of dumb, but it is what it is. Triode is like our NPN saturation where it's fully on, and saturation is like NPN forward active. So don't get that confused. I can, and sometimes you'll see on, as I look around on websites, they will get it confused, right? They'll call the triode mode actually saturation, which is not true, right? The triode mode is, they call the saturation mode saturation, like so it's just, they get it all confused, right? So now that you know the distinction, be very careful when you read other sources. Okay, so let's look at cutoff. We know what cutoff is. Cutoff is just off, no current. And so the way it works is I'm going to redraw our NPN or NMOS situation. It's when this gate voltage here is less than some VTO, or what we call the threshold voltage, right? And this threshold voltage is, let's just say, about 1 volt, okay? And so this is like a PN junction here that's going to be in reverse bias. Depletion regions form right here and no current flows. If you don't have enough voltage here, okay, if you don't have enough voltage here, and if you have positive pressure over here, look at this, you have plus, minus, right? Okay, so you have a positive at the end, right? And minus here, this is reverse bias, no current flows. So this is cutoff, okay, easy enough. Now, what about fully on? So in the fully on, we call it triode. Like I said, NPN saturation. And let's look at what's going on. So if we have enough gate voltage here, enough gate voltage bigger than the threshold, and we have some positive voltage here, right? We have to have some voltage here ready to go, VDS, okay? And we have to have this gate voltage as a super high. So this gate voltage, or minus the threshold, which, just ignore that, is greater than the drain source voltage, right? You are in kind of this super high voltage. Now you're going to get current to flow. And so what's happening physically? Well, imagine you're getting a charge buildup on this oxide plate. And look how you got this source attached to here, the body. And so you get this negative, right? So you have positive, negative. And you have a p-type material. And this p-type material, if you recall, all the little holes are being pulled to the right, which is the equivalent to having all these holes filled with electrons. So what do you have? You have a channel of negative charge carriers right here with no depletion region forming a path for current to flow all the way down. So that's kind of nice, right? Okay. Now the current equation is this nonlinear equation, right? And I rewrote it here. And what does it say? Some constant times 2 times essentially VGS, which is the gate voltage, times the voltage across here minus VDS squared. Okay, so well, let's assume that this is a small guy, right? Let's assume this is small. Well, what do we have here? We just have this term. And this looks a lot like Ohm's law, right? Where this term here is 1 over RDS on. Okay, or 1 over a resistor. And this resistor, what we will call is RDS on, right? So RDS on is the gate-dependent resistance found in data sheets, okay? And obviously the smaller is better. So what is this saying again? Let's repeat. I have a voltage VDS. I have a current that's going through this whole thing, right? You can think of this as like a resistor, right? And the smaller the resistor, the better. And I'm going to get a smaller resistor by having more voltage here, right? Can you see that VGS is inversely proportional to RDS? Okay, so the more VGS you put on here, the smaller that RDS on is, okay? And so if I look at the data sheet of like this guy here, RDS on is like in the milliohm range, right? So really nice, right? So that's something to look for when you're looking at a data sheet and you're trying to spec out a good MOSFET is you want to find a low RDS on, okay? But yes, it truly is nonlinear. However, this is kind of our engineering way to linearize it and kind of spec it out, okay? Now, what about the forward active, or now we call it the NMOS saturation? This is the kind of case where, you know, like I said before, we don't really care about it if we just want an on-off application, right? We really only care about these two things, cutoff and saturation, right? But if you want to kind of play with the voltage in somewhere in the middle, then what you have is something like this. So similar to this guy, if you have enough, you have a gate voltage that's bigger than the threshold, okay? But this time, VGS is now less than VDS, right? So this kind of flips, right? What happens? Well, what you got here is you have not enough VGS going on. And so what happens is this now behaves like a reverse bias diode like, right? And so your nice conductive channel that was nice and thick here has a little pinch off point, right? Maybe that's the easiest way I can think about it or communicate this. And so that means your conductive channel is reduced, right? And so now your current is just dependent on VGS. It's nonlinear, you have the square term, but you can see that if VGS is not larger than VDS, like in this one, ID is purely controlled by VGS, right? So in this case, you kind of get this like control and no VDS terms, independent of VDS, right? You still get that VGS control here, but now you're behaving much more like a kind of like a very nice resistor in some sense. Whereas here, it's all pretty much controlled by VGS, right? So that's the way you can see this is kind of like that throttling effect, right? Okay. All right. So these are the 3 modes, very similar to the bipolar junction transistor. And we will summarize these equations and do some examples in the next lecture. Okay. All right. Well, I hope you got a good understanding of NMOS and PMOS, some intuition, and I'll see you in the next lecture.